Hello everyone, this is Jason Kendall. Welcome to the next of my introductory astronomy lectures. Last time we were talking about the surface features of the sun. Now let's get down to the center of things, down into the core of the sun. So what's way down in the core of the sun? What are the conditions like in there? And we see from this diagram that it can be very complicated, but below the photosphere and below the chromosphere. Deep down in the sun, the conditions are really rather strange. So let's go see what's happening down there. So the sun's interior, which we call the interior structure of the sun, is divided up into a series of areas. The photosphere is very thin with respect to the sun's thickness. But then there's directly below the photosphere is what we call the convection zone, and it's an extraordinarily deep thing, 200,000 kilometers deep or so. Below that, we have an area called the radiation zone. It has nothing to do with radioactivity. No, it is just where energy is transported via radiation, and that's about 300,000 kilometers. And the core itself has a diameter of about 200, or radius of about 200,000 kilometers. And the sun itself is divided up in these sections. The convection zone is where energy is transported primarily through bubbles of gas that are hotter and then rise through, and radiation is where energy is transported this way. So let's actually look at the interior of the sun and what is down way deep in the core. In order to understand the depth and what it is way down in the core, we have to rely on a lot of physics. And so here we go, the beginning of lots of physics in this entire series. The major aspects of physics that we're going to be talking about first are the law of gravity, Newton's law of gravity, F equals gmm over r squared, the principle of hydrostatic equilibrium, meaning it don't move, and the equation of state, meaning how gases behave with respect to pressure, density, volume, etc., macroscopic variables you might measure about a gas, and some source of energy, meaning, the sun's radiating light, so therefore it must have something to replace that energy in the form of light, and then that energy's got to get from wherever it is produced out to the surface such that it goes out into space as light. So we're going to deal with these in the next series of videos, this one and the next two, in order to get there. But first, let's talk about hydrostatic equilibrium, which is a fundamental concept with respect to stable things. Hydrostatic equilibrium, blah, 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 blah. Hydrostatic equilibrium simply means that the sun isn't getting bigger or smaller. It's not squishing in on one side and then getting bigger on the other. It's pretty much stable in every way we can think, or at least as another way of saying it's really not significantly sloshing around. And as such, the sun, because it's in hydrostatic equilibrium and it's a big ball of gas, it takes the shape of a sphere. And so the best way to think about it is that the gravitational pull of all the gases, which has mass, gas has mass, people tend to forget that, but the gravitational pressure due to the weight of the gas must be balanced by the pressure pushing against that gravitational pull. So something's got to provide that pressure, and that pressure is the gas pressure. So gravity pulls all the gas in, and the gas itself provides pressure outwards. And so there's a balance. And in hydrostatic equilibrium, let's explain this now. The deeper you go, the greater the pressure must be. So the greater the weight on top as you go in, so therefore the pressure counterbalancing it must be greater. And this equation that we see, let's read it out because it kind of helps to read it. And it's in the form of a calculus-based equation where we're saying that the dP simply means a little change in the pressure. So that D means little change in, and the dr on the bottom is a little change in radius or depth. So there's a little change in pressure as it changes in radius or depth, and that corresponds to something related to Newton's law of gravity. And that's where that big G comes from, because that's the big G of Newton's law of gravity. The m is the mass of some element pushing down on top, and rho, that Greek letter rho that looks like a P, a kind of a funny shaped P, is the density of the material that has that mass of that region. And then r squared on the bottom is the distance from the center, so from the center of mass. Therefore, when it's in hydrostatic equilibrium, the balance in pressure means that it's not going to be pushing up or down, and it's not going to be sloshing up or down. It'll be all in balance, and so you can measure how the pressure changes with depth by simply knowing what the mass of a little element is in there and its density and where it is inside of there. That's what we really care about. That's hydrostatic equilibrium. And it means that the weight that is pushing down on top of a little element is being pushed back up by the pressure from below. So in hydrostatic equilibrium, if you kick the star just a little bit, what happens? Well, if the pressure dominates, meaning pressure outward, something below, then the star will expand. And if gravity dominates, it'll contract. So it depends on what you do. If the gravity then dominates, it'll contract a little bit and expand, and therefore, that if it contracts a little bit, it'll go until the pressure then pushes back, and then the pressure pushes back and expands, and then it might then say, ooh, well, there's not enough pressure to hold the gravity, so it'll contract a bit. So there's this oscillation that then gets balanced out in hydrostatic equilibrium. And eventually, when you think about this, as it oscillates between pressure pushing out and gravity pulling in, eventually it settles down. And when it settles down, you eventually get a setup where then the core is very, very, very hot and very dense and really compact, and surrounded by a much, much cooler, much lower density envelope around the core. And that's kind of what you get after a long period of, or a relatively long period of time, where the hydrostatic equilibrium is established inside a star. So let's look at that really carefully, and we'll kind of see it one more time just for fun. And so we got the blue arrows representing gravity pulling in and the gas pressure pushing outward. And so as you go deeper, we started the whole thing, and we say as you go deeper, the pressure increases as the gravitational force increases too. So the deeper you go, the greater the pressure. So most stars, so how does the pressure vary inside of there? What is the thing that says what the pressure is? And we can go back to old high school chemistry with the ideal gas law. And the ideal gas law is what we're going to use in order to determine the relationship between the pressure, the density, and the temperature of the gas inside the star. So that is a very good approximation to exactly what's happening there, because it's pretty much every particle inside of a star is just is essentially a single particle. And so we can use the ideal gas law as for the incredible range of temperatures that are inside a star and densities that are inside a star. So if you compress a bubble of gas, the pressure goes up and the temperature goes up. And if you let it expand, the pressure goes down and the temperature goes down. And so those relationships of the ideal gas law exactly tells us how the interior effects go in the star. So the bottom two equations are equivalent. Let's look at the left-hand one. Those brackets mean the average of, or average pressure. The bracket around the row on the right-hand side means the average density. And the little m with a hat over it, or the dash over it, means the average mass of the particles of the gas. And kT is the expression of the energy of a particular particle in the gas. So K is the Boltzmann constant, and T is the temperature. Now, on the right-hand side version, we have the pressure again, but a pressure at a particular area, and V is the volume pressure of a packet of gas, and V is the volume of that packet of gas, and that's simply equal to the total number of particles in that gas times kT, which is basically the energy of each particle. So the pressure times the volume of a particular packet of gas depends on how many particles are in it, and their temperature is what the ideal gas law really says. So I broke it out here in a whole bunch of different ways to give you the exact definitions for each. And there's some things to play with, is to say what happens when you make something hotter. If you keep everything constant, what's got to happen? Let's say you keep the volume fixed and you make it hotter. You keep the total number of particles in the box the same, the volume's the same, you make it hotter. Well, of course, the pressure goes up. If you apply greater pressure on the outside of the box, and you don't change the volume, then the temperature must go up. And if you expand the volume, what happens? And if you add more stuff, more particles, what happens? And so you can play like a mixed game and say what things can happen if you do this and then you do that. And the Boltzmann constant is a thing that relates it's specific to the entropy, means more specifically the ways that you can arrange the gas particles inside of the box is really what the Boltzmann constant comes down to. And that relates to the energy per particle at a given temperature. So the ideal gas law says you got particles in a box under pressure at a temperature. How big's the box? How many particles are in the box? and it relates to either all of them. And it implies that all the particles are roughly the same in size, or they can be averaged to their size scale. And that's what the ideal gas law says, that these particles, when they hit each other, they bounce off of each other, they don't transform, they don't become other particles, they don't stick. They just kind of reflect off each other. Think of them as billiard balls bouncing around inside a box. That's a good way of thinking about the ideal gas law. So let's take the ideal gas law and apply it to this core envelope structure of a star, such as the sun. And the deeper you go into the star, the greater the pressure. And the ideal gas law says that if you put it under pressure, then it must be hotter and hotter and hotter. And so down in the core of the star is going to be extraordinarily hot, much hotter than the surface. And that's just what we expect. And the central temperature then, it's a really interesting question. What is the central temperature? How hot is it down there? Well, the central temperature has what we call thermal energy. And thermal energy describes, when we say thermal energy, we mean the average motion of particles inside the core. And the thermal energy has to be high enough per particle that it supports the weight of all the gas on top of it. And the only way for it to do that is for it to bounce around really fast. And by bounce around really fast, we mean move really fast. And if it's got to be moving really fast, it's got to be really hot. If we equate that thermal energy, which is 3/2 kT, to a typical a typical proton, which is what most of the sun is made out of, down in the core, and to the gravitational energy it has by being there, which is the gm sub proton, which is little p, and then compared to the entire mass of the sun, which is the m sub sun, divided by r sub sun. And so we're just saying the gravitational potential energy of a proton at the center of the sun, which is the right-hand side of the equation, and we set it equal to the thermal energy, the average thermal energy at the core of the sun. That's why the temperature sub C, meaning core, and then the little the O dot, which is the sun's symbol. So we're saying, what's the temperature at the core? We know the mass of the proton, we know the mass of the sun, we know the size of the sun. And so if we put all that together, we get the central core temperature as about 15 million Kelvin, which is extraordinarily hot. We then say, well, what's the pressure there? And we can justify the central pressure by saying, well, what is the pressure down there? And we can take that hydrostatic equilibrium equation and then merge it with what we call the mass continuity equation, which is the little one that I put there in the upper right. And those two things merge together and just put them together as like the total sun value. So replace the dP with the pressure C sub sun, and replace the dr with the radius of the sun, and replace the m with the mass of the sun, and the rho with the density of the sun, etc. And what we get is that approximate value that we have in this equation, which says the pressure of the center of the sun goes roughly like, and that's what those equivalent symbols mean. That's what those double twiddles or double wavy lines mean. This means the pressure at the center of the sun is approximately the gravitational constant, that's at g again, times the mass of the entire sun squared divided by the radius of the sun squared, the radius of the sun to the fourth power. And that's a rough approximation by taking these differential equations that we would use in calculus and integrate through using a computer, in fact, and just assigning them their global values. And that gives you an enormous central pressure. And it's like 10 to the 16th pascals, which is, wow, a billion is 10 to the 9th. So it's 10 million billion pascals. And that is more than 100 million times the pressure at the bottom of the Mariana Trench. So yeah, it's pretty high pressure. By comparison, at sea level, the normal air pressure at sea level is about 100,000 pascals. So it's over 100 billion times the pressure at sea level. It's pretty high pressure, an extraordinarily high pressure in order to support the weight of the sun on top of it. So now we have the central temperature, we have the central pressure. Now we can measure the density of the center of the sun, and we can go back to the ideal gas law, plug that in, and determine the central density. And we end up with, if we plug in the central values for the pressure and density, we get for the pressure and temperature and give it a typical mass, which is a mass of a proton, we find that the density is on the order of 150,000 kilograms per cubic meter. Now, gold has a density of about 10,000 kilograms per cubic meter, roughly. And so, therefore, it is 10 times more dense than gold in the center of the sun. But it's still a gas, which is really crazy. We think about gold as being a solid, right? And it is at room temperature on Earth. But remember, the sun stays as a gas because, well, it's so incredibly hot. It stays as a gas even though the density is much greater than that of gold. And gold is one of the most dense objects that we know, which is really interesting. So the central density of the sun is extraordinarily large. And we can use these basic arguments to argue that this is what the central density must be and what the central temperature must be. And this was done well before, the invention of computers and computing algorithms that would compute the central density and so forth. The core conditions are, the core is about a quarter of the entire radius of the sun. The temperature is about 15 million Kelvin, and the density, for more specific calculations, is about 151,300 kilograms per cubic meter, compared to the surface, or roughly the envelope, or maybe just the photosphere, which the radius is about 700,000 kilometers, and temperature is much, much cooler at 6,000 Kelvin. And the density is so it drops off really rapidly from the center to the surface. And that's just by comparing using the ideal gas law, the equation for hydrostatic equilibrium, and the fact that there's no gaps in the stars, that mass continuity equation. We just put that together, and that's what we get as some really basic things. And because this is just simply hydrostatic and some basics of ideal gas law, this was actually understood very long before understanding how this gets that hot and how it maintains that heat. So let's actually look now more detailed, and if we then go in a more detailed description of, how does it drop from the core to the surface? Well, we know that it can't just go like, here's the core value and here's the surface value. It has to drop off in some way. So again, we start at the core, it goes through the radiation zone, convection zone, and the photosphere, and then we can just dial down and say, okay, the center is the central line, and there's a peak at the center. And so we see that most of the high density area is right at the center. The densest portion of the sun it's extraordinarily high density, and then it drops rather rapidly about outside the core. So the core itself is where most of the high density area is, and the envelope structure is right outside these peaks when it's very, very low density. So in fact, it gets to be about the density of the surface of the sun well at about halfway out the radius of the sun. So the density that's about halfway out the sun is almost the same as at the surface, the photosphere, which is interesting. So it's extraordinarily high density at the core and drops off rapidly once it gets outside the core. Now then we can say, how does it vary with the temperature? The temperature, however, more smoothly varies. It still is strongly peaked in millions of Kelvin from the center, and it goes out to about 6,000 at the photosphere. But yet you can see that the temperature drops rather differently. So between these two things, between the steep difference in density and the smooth difference in temperature, there comes a point when you have that could actually draw out convection. So convection is when you have a strong temperature gradient, but not a very strong density gradient. And then that is ripe for conditions of convection. And that's what we saw on the surface of the sun, is enormous granulation and supergranulation, which is the convective cells. So what exactly is convection? Well, we'll get to that really soon. And what are the other things as well? How the sun transports energy in the core. It transports by light just simply bouncing from place to place, and that's the fastest way for it to get out. And then as soon as it gets up to roughly the surface, or about halfway out, the convection starts to come in, where the best way and most efficient way to transfer energy from inside to out is that bubbles get hot and bubbles rise and fall. And so that's about 2/3 the way out from the center, about 200,000 kilometers from the surface down. So that's how the energy is transported from the interior out. How do we know that this is even true? Well, we can actually look at the surface of the sun, the photosphere, and see that it's actually roiling, rising and falling. And then we can map how those roiling, rising, and fallings occur, and we see that the sun is actually kind of ringing like a gong. And that ringing is waves that start at the surface, go deep inside, reflect off the interior or higher density regions or higher temperature regions, and then reflect back to the surface. And so what this diagram is showing in letter A is that there are oscillations that occur on the surface of the sun, kind of like a spherical drum or a sphere, just kind of a ringing sphere. And the right-hand side image is saying that as the waves travel deep from the surface, deep down in, they get to a hot spot and then refract away from that hot spot. And that's very similar to what happens in a mirage in the desert. So if you have a very, very hot surface like a road in the desert, you get this double image, and it's a refraction of light because of the change in density and change in temperature. And so waves of pressure can actually be refracted as well. And the different kinds of waves and how they are incident upon the surface gives a distinct pattern on the surface. How they go down through the sun gives distinct patterns of what wavelengths are allowed, and that actually allows us to map the interior. And that process is called helioseismology. And helioseismology is the study of the surface of the sun and its motions up and down. And in this image, which is taken by the Solar Dynamics Observatory, what we're looking at is a speckly sort of funny image, and the dark dots are upwellings, and the white dots are where the things are moving down. So this is what's called a Dopplergram. Okay, so we'll see it again. I think it'll loop. There we go. Good, it loops. And the Dopplergram shows that the dots that are coming up, which are dark, are coming towards us. The dots that are white are going away from us. And in the center of this image is a sunspot. You can see that it's kind of stable. But look for a second at kind of the static-y sort of feeling of the surrounding areas. You can almost see what the granulation looks like, which is kind of the lumpy bits, because the white is going down and the black is coming up. So you got these kind of lumpy sort of objects. But then you might be able to discern sort of wave-like patterns inside of this. And in fact, with large computer algorithms, you can. So you can determine that over the large scales, you get extraordinarily big wave patterns that you can then map how they reflect off of the interior structure of the sun. And so Solar Dynamics Observatory has the capacity to see this Dopplergram across the entire surface of the sun. And the left-hand side of this image is a Dopplergram taken by the Solar Dynamics Observatory, and the right-hand side is the sun in visible light at the same time. And so we see that there's motion up and down with respect to the sun, and this can be mapped to the interior structure. And that allows us to determine the interior structure of the sun and say, oh yes, the model that we just showed you in those other things, how the density and temperature maps inside, can have an exterior appearance. So motions on the surface are dependent upon the interior conditions, specifically the temperature and density. And that study is called helioseismology, and it allows us to understand the center of the interior of the sun. Not all the way down to the core, but to some extent it does. But the core is measured in a slightly different way, if it can be measured, because nobody's ever been to the sun. Nobody can get to the sun. You can't get to the sun, take a scoop. All you get is light. And so therefore, we have to be able to see the surface patterns and understand them. And so seeing those wave patterns on the surface of the sun and how they actually bounce around tells us about the interior of the sun. All right, so there we have it, and we will see you next time on our next bit when we're going to talk about exactly what those convection cells are and all that kind of thing, and how energy gets transported, because, hey, the sun's cooling off, and at some point, it's got to replace that energy. We'll see you soon.